we would like to have an expression for the gravitational potential energy of a rigid body represented by a continuous mass distribution, such as this body here, this lump of matter with an arbitrary shape taking up a volume in this three-dimensional space. So I've placed it above the xz plane, and we'll let y be the vertical direction such that y equals 0, our reference plane is down here. Now, if the body was just a point mass, then we'd have a simple expression for its gravitational potential energy, just its mass times little g times the height of that point mass above or below our reference plane. But because it is a body, it has different parts of it at different heights above our reference plane. So how do we find the total gravitational potential energy if there's not just one unique value of y? Well, the idea will be to represent this mass as a collection of an infinite number of infinitesimally small little bits of mass. These little red cubes here are imagined to be like tiny little bits of the body, infinitely small little volumes, each with a tiny mass dm. So the tiny little mass dm we could model as if it were just a point mass at this one specific location, with the gravitational potential energy depending on its height above our reference plane here. And so if we can find the UG of one of these little bits of mass, and then add all those bits of UG up, we would get the total. So that's exactly the plan. The infinitesimal gravitational potential energy, dUg, as in a very tiny amount of UG, associated with an infinitesimal bit of mass dm, can be given by our usual point mass type formula. So the tiny little bit of mass times g times the height of that little bit of mass above our vertical reference plane here. So we would like to sum all those dugs to get the total ug for the whole body. So if we're adding up an infinite number of infinitely small things, then we are integrating. And as for our limits of integration, I'm going to write the word body underneath our integral sign, indicating that what we're going to do is add up the contributions from every little bit of mass in the body, making sure to count each little piece of mass once and only once, and not miss any bits of mass and not double count any bits of mass. So we're going to get the whole body, exactly the whole body, in this sum here. So each little bit of gravitational potential energy for some little bit of mass is given by this formula here. So we'll plug that in. And little g is going to be the same for every single little bit of mass if we're in a uniform gravitational field. So little g is a constant with respect to this integral, and we can pull it out front right there. And we're left with just this piece here, this integral of the mass of each little bit of mass times its own y-coordinate added up over the whole body. Okay, so we need some way to evaluate this term. And here's where we'll go to our definition of the center of mass, or the y-coordinate of the center of mass of our body in particular. There will be a center of mass. Its y-coordinate is given by this expression here, or would be if we had a discrete mass distribution. If we have a continuous mass distribution, then these sums get replaced with integrals. And the numerator here we recognize as being exactly the term that we wanted to evaluate over here to find the total gravitational potential energy. So the numerator here can be expressed as the y-coordinate of the center of mass times the denominator. And these denominators we see are just the total mass of the system, or the total mass of our body, the sum of all the little bits of mass. So the total mass of the body times the y-coordinate of the center of mass is identical to this integral here. So we will replace that integral with the y-coordinate of the center of mass times the sum of all the little bits of mass over the whole body, or in other words, the total mass of the body, leaving us with a simple and familiar expression. Apparently, the total gravitational potential energy of the body can be expressed with a formula almost identical to that of a point mass. We just need the total mass of the body, little g, and the y-coordinate of the center of mass. It's as if the whole body could be represented by a single point mass located right here at the CM at a distance ycm above our reference plane.